So the first thing we're going to do is review what an antiderivative is. That says a function capital F is an antiderivative of lowercase f on an interval I when capital F prime of x is equal to lowercase f of x for all x in I. So remember, an antiderivative is exactly what it sounds like. It's the opposite of taking a derivative. You're going the other way. For each of these functions over here, you just have to think, what function did I take the derivative of in order to get this function? And that's the antiderivative. Remember, we add c, this constant of integration, anytime we are taking an antiderivative to account for any constant that could have been there when you took the derivative of this function and got this one over here. Now remember, the antiderivative is also called an integral. And when you take an indefinite integral of a function with respect to x, that's what this means, you need to take the antiderivative of that function. So here, you're taking the integral of f of x dx, meaning that you're taking the antiderivative of f of x. And it's capital F of x plus c. This is the antiderivative of this function plus the constant of integration. Anytime you take an indefinite integral, you must add c. Now, a differential equation in x and y is just an equation that involves x, y, and the derivatives of y. So let's say you have a function and you take the derivative of that function. Then that new equation that you have is a differential equation. So if we had y is equal to x cubed and took the derivative, we now have y prime is equal to 3x squared. And this is a differential equation because we have the derivative of y. Here, dy dx is equal to 1 over x. The derivative of y with respect to x is equal to 1 over x. This is a differential equation. Anytime you see y prime dy dx or f prime of x, something like that, is equal to a function, that's a differential equation. Now, the general solution is the family of all antiderivatives of a given differential equation, written as a function plus c. So here, if you have a differential equation and you want to take the integral of this or integrate this, you find the antiderivative of this function right here. So what's the antiderivative of negative sine of x? That would be cosine of x. And then you add c because you need the constant of integration to account for any constants that were in that original function when you took the derivative of it. Now, anytime you have a function plus c, when you've solved a differential equation, that is the general solution. The particular solution is the antiderivative of a differential equation where an initial condition is given, allowing you to solve for c. So if you solve a differential equation and you see y is equal to a function plus c, that is the general solution to your differential equation. If you wanted the particular solution, they must give you an initial condition. So here they say dy dx is equal to negative sine of x, where f of 0 is equal to 2. That means that you must integrate this particular function right here, this differential equation. And when you integrate, you find the general solution, which would be y is equal to cosine of x plus c. Once you find this, then you can use your initial condition, f of 0 is equal to 2. So you plug in 0 for x, 2 for y, and you can now solve for c, which is equal to 1. Same thing here. You took the antiderivative in order to get the general solution, or you took the integral in order to get the general solution. Now you use your initial condition, plug in 4 for x, 1 for y, and you can solve for your c, which would be negative 1. That is the particular solution. Next, we're going to talk about how to solve differential equations. So the first thing you want to do is separate the variables. You want to get all the x's on one side, all the y's on the other side. Get all the t's on one side, get all the q's on the other side. Once you do that, you can then prepare both sides for integration. That means you want to separate the function that you are integrating based on the number of terms, so you can give each term its own integral. You can then use the constant multiple row, bring all the constants out front, just get it ready to integrate. Once you do that, then you can integrate and add c, and that will give you the general solution. But if there's an initial condition, that would be step 4. You plug in your initial condition to find c and get your particular solution.
Time to flap those wings! It's example time!
Now example 1 says find the general solution of the differential equation and check the result by differentiation. So here we have our differential equation. What we need to do first in solving a differential equation is separate the variables. This is super important. You get points for this on the AP test. So first thing you do, you need to separate the variables to get all the y's to one side, all the t's to the other side. So to get this dt over here, I multiply both sides by dt and I'm done. Next, I prepare both sides for integration. So I'm going to integrate both sides of this equation. Now over here, this is good. This will just become become y. Here, I need to prepare this a little bit more, so I use the constant multiple rule, take this 9, move it out front of the integral sign, and I am ready to integrate. When I integrate, again, over here, this is just going to become y. Here, when I integrate, I'm going to use the power rule. So this is going to become t to the 2 plus 1 over 2 plus 1, or t to the third over 3. Multiply that to the 9 out front, and don't forget to add c. Now, if we simplify this a little bit further, the 9 times the t cubed over 3 becomes 3t cubed plus c, and we have our general solution. Now, the question is, did they give us an initial condition? No, they just gave us the differential equation. Therefore, we can say that y is equal to 3t cubed plus c is our answer. This is our general solution. We can check the result by differentiation. If we look at this and take the derivative of both sides with respect to t, over here we get dy dt. Here, when we take the derivative with respect to t, this is going to become, when I bring the 3 out front using the power rule, 3 times 3, t to the 3 minus 1. Over here, this is going to become 0, so that would be 9t squared plus 0, and that is exactly what we started with, so we got the correct answer.
Time to follow my pheromone trail back to the hole. You try.
Okay, again, solving a differential equation. The first thing you need to do that you get points for on the AP test, separate the variables. So multiply both sides by dx to get the y's on one side and the x's on the other side. Done. Next, what we can do is prepare both sides for integration. So I'm going to integrate both sides of this equation. Now, if you recall, when I'm integrating something over x to the first power, I'm not going to bring it up to the numerator. What you do instead is you make this 2 times 1 over x and bring that 2 out front of the integral sign. And I am ready to integrate. One of our special integrals, the integral of 1 over x, is equal to ln of absolute value of x plus c. So we integrate both sides. This just became y. Once we integrate that, we get 2 times the natural log of the absolute value of x plus c. Don't forget to add c. And we have our general solution. Now again, did they give us an initial condition? F of 0 equals 2 or something like that? No. Therefore, we just leave our general solution as our answer. We can then check our answer by taking the derivative of both sides with respect to x. Over here, this is going to become dy dx. Here, when I take the derivative of 2 ln of x plus c, the 2 comes out front by the constant multiple rule, and the derivative of ln of x is 1 over x. So 2 times 1 over x is 2 over x, which is exactly what we started with, so we got the correct answer. Now, example 2, if you notice, this says find the particular solution that satisfies the differential equation and the initial condition. So it gives you an initial condition this time and a differential equation. So everything is the same steps. First, separate the variables. They give you points for this on the AP test. I can't stress this enough. Get all the y's to one side, all the x's to the other side. So instead of writing y prime, what we're going to do is write dy dx. That shows you that you have to multiply both sides by dx, and now you have successfully separated the variables. We have the y's on one side, the x's on the other side. Next, we're going to prepare both sides for integration. Now, if you recall, when we integrate a function with multiple terms, we need to integrate both terms individually. Here, we can use the constant multiple rule and take that 10, move it out front, move the 12 out front, and now we are ready for integration. So we're going to integrate and add c. So here, the integral of x to the first is going to be x to the 1 plus 1 over 1 plus 1, or x squared over 2. The integral of x cubed is going to be x to the 3 plus 1 over 3 plus 1, or x to the 4th over 4. Don't forget to add c. Now, let's simplify these fractions, and we end up getting our general solution. After we find our general solution, we need to plug in an initial condition if it's provided. It is in this case. We have our general solution. Now we need to find our particular solution. So we take our initial condition and plug it into our general solution. So 3 goes in for each of the x's, 2 goes in for the y. Now we can solve, and when we simplify this, we end up getting that c is equal to 200. This is not your answer. You need the particular solution, which is the general solution when you plug in your value of c that you found with the initial condition. All that's left for you to do now is to rewrite this in standard form. So take this negative 3x to the 4th, move it out front, and you are done. This is your particular solution to this differential equation with this initial condition.
Red ants are scary. You try.
So let's go ahead and solve this differential equation. First thing you're going to do that you get points for on the AP test, separate the variables. So instead of f prime of x, we're going to write dy dx, and we write our function over here. To separate the variables, we multiply both sides by dx. We have now successfully separated the variables. We got the y's on this side, the x's on this side. Perfect. Second step, prepare both sides for integration. So I'm going to integrate both sides of this equation. Now, this side over here, we have a constant multiplied to our function. So we're going to take that 4, move it out front using the constant multiple rule. And now we are ready for integration. So we're going to integrate and add c. Integrate dy, and we get y. Over here, the integral of e to the x is e to the x plus c. Multiply that by 4, you get 4 times e to the x plus c. We have now found the general solution to our differential equation. But we are not done because this question gives us an initial condition. Using that initial condition, we can now find the particular solution by plugging in 0 for x and 3 for y. So when we plug those in, e to the 0 is 1, 4 times 1 is 4, and then subtract 4 on both sides, you get c is equal to -1. That means your constant of integration is equal to -1, which we can plug in to our general solution to find our particular solution. And you're done. Now, example 3, everything is the same except it gives you f double prime of x is equal to 2. So it gives you the second derivative of our function, and it gives you 2 initial conditions, one for f prime and one for f. So you're going to do exactly what you think you would do. You're going to integrate using the process that we talked about earlier. We're going to solve this differential equation, find the general solution that goes with that, and then plug in this particular solution. Then you will do the same thing all over again. You will integrate and then find the general solution that goes with that and plug in this initial condition to get your final answer. Okay, so we basically are just doing it twice. So first thing you do, separate the variables. So this again is not dy dx, it's the second derivative. So what we do is we multiply both sides by the denominator, and we now have our variables separated. Next, we're going to prepare both sides for integration. So we integrate both sides. When we integrate this side, it's just going to be dy dx. Over here, the integral of 2 is going to be 2x plus c. So we now have the first derivative. We take the initial condition that we have here. We're going to plug that into our function here. So it says f prime of 2 is equal to 5. So we're going to take 2, plug it in for x, take 5, plug it in for f prime or dy dx. Now we can simplify this and we get what our value of c is. It's 1. So we take this 1, plug it in for c here. Now we have f prime, the equation for f prime. So we're going to do the same thing all over again. We separate the variables. So instead of f prime, we're writing dy dx. Multiply both sides by dx, and we now have our variables separated. Next, we can prepare both sides for integration. So we're going to integrate both sides. Here, since there's multiple terms, we have to integrate each term. We can then integrate and add c. So let's go ahead and integrate both sides. This becomes y, this becomes x squared over 2, and this becomes just x plus c. We can then simplify this, and we have the general solution to our given differential equation, this one right here. Now, the last step would be to solve for our c using this final initial condition. So we take 2, we're going to plug it in for x here and here, and we're going to take 10 and plug it in for y right here. We can then simplify, and we can get that c is actually equal to 4. So we can take 4, plug it into our general solution here, and we get our particular solution.
Now example 4 says a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving the height s as a function of time t, and determine when the ball hits the ground. Reminder, acceleration due to gravity is negative 32 feet per second squared. Now this may not look like it, but this example is actually just like example 3, in that you are given the second derivative equation and you're given 2 different initial conditions, one that corresponds to your original function and one that corresponds to your first derivative. Now in this question, it's key to understand what we talked about earlier this year, in that the position function, if I take the derivative of that, I get the velocity function. And if I take the derivative of the velocity function, I get the acceleration function. So it would make sense then that if I take the integral of the acceleration function, I should get the velocity function. If I take the integral of the velocity function, I get the position function. So that's how we're going to end up solving this particular example. So let's go ahead and state our initial conditions. We have 2 initial conditions, one that deals with our position and one that deals with our velocity. So our initial condition that deals with position would be our initial height. And that says our initial height is 80 feet, meaning at time t equals 0, our position function s is going to equal 80. We also have an initial velocity of 64 feet per second, meaning that at time t equals 0, our velocity function, which recall is the derivative of your position function, so instead of s, it's going to be s prime. At time t equals 0, s prime is going to equal 64. Now, what is our second derivative equation? Well, it tells us that acceleration due to gravity is negative 32 feet per second squared. And since we're just throwing this ball upward with an initial velocity of 64 feet per second, the acceleration due to gravity gravity is going to be the same the entire time. So we can say that our acceleration function, the derivative of our velocity function, or s double prime of t, is going to equal negative 32. So the way that I'm going to find my position function is I'm going to integrate this particular acceleration function to get my general solution for my velocity function. Then I can find my c value by using this initial condition. Then I can integrate that velocity function to get the general solution of my position function. And I can use this initial condition to solve for c. So that's how we're going to do this. So let's go ahead and solve this differential equation. Remember, the first step in solving a differential equation is to separate the variables. You will get points marked off on your AP test if you do not separate the variables. You have to do this. So if we have our second derivative is equal to negative 32, to separate the variables, I just have to multiply both sides of the equation by this denominator over here. Now I have the s's on one side, the t's on the other side. I have separated my variables. The next step is to prepare both sides for integration. So I'm going to integrate both sides. Anything I have to do? Well, I could take this negative 32, move it out front if I wanted to, or I could just leave it like this and move on to my next step where I integrate both sides and add c. When I take the integral over here, this becomes ds dt, the first derivative of s. When I integrate over here, this becomes ds dt. When I integrate over here, remember the integral of a constant, I just tack on a t. So this is going to become negative 32 t plus c. I have now found my general solution for my velocity function, but I am given an initial condition, meaning I can solve for my particular solution for my velocity function. So all I have to do is take 0, plug it in for t, take 64, plug it in for ds dt, and now I can solve for c. So to solve for c, all you have to do is just multiply these together and you get c is equal to 64. So I take that 64, plug it in for c in my general solution for my velocity equation, and I have my particular solution for my velocity equation. Now remember, I'm looking for the position function, so I need to integrate the velocity function. So I'm just going to do exactly what we did to our acceleration function, but this time with velocity. So let's integrate this. Remember, to solve a differential equation, the very first thing you have to do is separate your variables. So s prime of t is the same as ds dt. These both mean the first derivative of s with respect to t. So what I'm going to do is get all the s's on one side of the equation, all the t's to the other side. So I'm going to multiply both sides of the equation by dt. I have now successfully separated my variables. Next, I am going to prepare both sides for integration. So I'm going to take the integral of both sides of this equation. Now remember, on this side, I have a function with multiple terms, meaning I have to take the integral of each of those terms separately. Now what I have to do is use the constant multiple rule, take this negative 32, move it out front of the integral sign, and I have successfully prepared both sides for integration. Next, I actually have to integrate both sides and add c. So when I take the integral of ds, I just get s. When I take the integral of t, I get t squared over 2. When I take the integral of 64, I get 64t. Remember to add c. Now what I do is simplify. Negative 32 times t squared over 2 just becomes negative 16t squared. And I have found my general solution for my position function. But remember, I'm given an initial condition. My initial height is 80. So at time t equals 0, I know my height is 80, meaning I can use that initial condition to find my c value. So I take 0, plug it in for t here and here. I take 80, plug it in for s, my position, here. Now I solve for c. So this times this, that's 0. This times this, that's 0. So I just get c is equal to 80, meaning I can take 80, plug it in for c in my general solution up here, and I have found my position function. But if you recall, that wasn't the only thing it was asking you to find. It also wants you to determine when the ball hits the ground. So to do that, we're going to take this position function and we're going to plug in 0 for the height, because if the height of your ball is 0, that means the ball is hitting the ground. So I take 0, plug it in for s, and now I can solve for t, the time when the ball hits the ground. So how do I solve this for t? Well, I can factor out a negative 16 from each of these terms, and now I have a quadratic trinomial that I know how to factor. I can use a magic x, I can use box method, I can use guess and check, factor by grouping. However you do it, we end up factoring t squared minus 4t minus 5 into the quantity t minus 5 times the quantity t plus 1. Remember, that's still multiplied by negative 16. So how do I solve this for t? Well, I can actually divide both sides by negative 16, and now I can solve this by using the zero product property. This times this equals 0, which means either this is equal to 0 or this is equal to 0. Here, I add 5 to both sides, I get t is equal to 5. Here, I subtract 1 from both sides, I get t is equal to negative 1, meaning I have two solutions, or do I? T equals negative 1, that means negative 1 second after I throw the ball hits the ground. No, that doesn't make any sense, so I'm not going to use negative 1 as one of my answers. Instead, my only answer is t equals 5, meaning 5 seconds after the ball is thrown, it's going to hit the ground.